We're going to look at how symmetries arise in LLMs. So this video is very mathematical. We're going to be looking at the internal machinery of a transformer from a mathematical point of view. And we're going to look at how group structures are used to encode position and distance about tokens. We're going to look at specifically how SO2 groups are used inside of LLMs to get semantic information. So this is a very mathematical point of view of looking at symmetries in an LLM. So I'll go over the basics, definitions of the mathematics itself. So the idea of groups comes from abstract algebra, comes from a mathematician called Galois. Groups are used to the groups model symmetry. So here's an example of a group. Let's look at a very simple example of a group acting on a square like this. Here I have a square, and I can rotate this square 90 degrees, and I could also rotate it 180 degrees. I could also rotate 270 degrees, and when I do so, there are certain things that are invariant, so that don't change. For example, the angle doesn't change, the shape doesn't change, the length doesn't change. So this is an example of rotational symmetry. There are other types of symmetries like, there's also reflective symmetry where you flip along an axis an object and it mirrors the other side of it. So that's an example of a reflective symmetry. This is rotational symmetry, and we could all model that with groups. So this is an example of applying a group. What is the group that I'm applying here? So I could create a set of elements, and these elements are degrees, radians of rotation, 0 degree, 90 degrees, 180 degree, 270. So there, I could define some type of a operation, which is a composition that combines two angles together. So here are two angles that are being combined by an operation, and the composition is following some set of properties, some attributes. So closure, associativity, identity, inverses. So whenever you have a group of elements, and they could be anything like the integers, and I could have addition as my operation, I could have some composition, some way to combine them. And if that operation behaves in this way, with closure, associativity, identity, inverses, then you have a group. So in abstract algebra and group theory, we don't really care about how the mechanics of the composition, how that's done. We care more about whether the operation itself behaves this way, whether it has these attributes, these properties. Whenever you do so, you take the group and the composition, then together you have a group. And you could apply that group. In this case, we're applying that group to the square, and the square is represented by a space. So this is represented by a set where we have a number of points, x, y, and R2. And I could apply a group to it. And whenever I do so, it's called a group action. And this is a function, the Cartesian product, where I take an element from G, which is an angle, and I apply it to a point in X, so I'm rotating, and I get a new point, right? And I'm doing that for all those points in this space to get to perform this group action. So I take G, and then I take the XY, a point in the space, and I get a new point. When I apply this group action. And what you'll see is that in an LLM, there's this same idea in LLM. There's a group action that's being used, which is it's the SO2 group. So this is an example of a type of group called a cyclic group. It's the C4 group. And it's a very simple group. So now let's look at how LLMs utilize groups. So in order to do so, we need to look at LLMs and the internals of it from a more of a mature mathematical way. So there are a lot of papers. I like to look at LLMs from the point of view of like Hilbert spaces. So The operation that you see in the attention, for example, are linear operators on this Hilbert space. A Hilbert space is a vector space that has an inner product defined on it. It's used in quantum mechanics. It's also used in transformers. There's a wide variety of applications. So in an LLM, you have a matrix, you have an embedding matrix. So what you're doing is that you have a set of tokens, you're mapping them to a vector space, and you have this embedded matrix at the end of it. And it has a set of vectors with components. So let's look at a very simple toy example of an embedding matrix. So we have here R 6 by 4. So 6 is the vocabulary size in this example, and then 4 is my dimension, is the number of components that each vector can be represented by. And this vector space has bases, which is orthonormal. And when you look at the number of dimensions, it varies. So in GPT-2 is 768, and about 12,288 in GPT-3, and the number increases for different LLMs. And what that dimension means is the number of components, that number of basis vectors in my vector space, or the number of components I have for a vector. So what this means is that what this is an example of in machine learning is an example of a finite Hilbert space. So the Hilbert space, so here's what I mean by that. Now, here's a vector. This row represents a vector. And this example is very simple. It has 4 components to it. So a Hilbert space basically is a set H, which is the vector space, and some inner product, which is the second, element right there. So Hilbert space, the H is basically a set. It doesn't have to be finite. It could be infinite, and these are elements of it which are vectors, and the vectors, the components of it are over a field. It could be real numbers or complex numbers. So in quantum mechanics, it's complex numbers. In transformers, you have real vectors, real numbers are used. And in an LLM, it's finite. You have a finite number of vectors just because you have a vocabulary size, right? Associated with it. So it's not infinite. This is a finite Hilbert space, and it's over R. It's over the real numbers. So uh so you have the field, which is the real numbers, and this is a finite um real Hilbert space used in an LLM. So what we look at next is how do you combine in this Hilbert space 2 vectors? And you do so by using a dot product. So there's an inner product defined on it. This is a complete inner product. And in an LLM, the type of inner product that's defined is called the Euclidean product. And it's where you take the components of 2 vectors, and you multiply them, and then take the sum of them, which is what this is. So this is the Euclidean inner product. This inner product is used, for example, when you do attention, for example. So whenever you have a vector space with a inner product defined on it like this, you have a Hilbert space. This is utilized inside of an LLM. And let's look at now. Next up, that's an example right there where Q is a query and K is another matrix. So I'm doing an inner product right there to get a new matrix right there. Sorry, to get a new vector right there. So this is an example of that Euclidean inner product being utilized. So the vector spaces that we're mapping the tokens to are Hilbert spaces, real Hilbert spaces, finite ones. And what this allows you to do when you look at things this way is that it gives you a framework of how to think about the internals of an LLM, like for people who are mathematically inclined, like myself, who have more of a mathematical background. So, and there are also papers that are written about this that look at, Hilbert spaces, so in an LLM context. So, how do we look at now? What are the groups that are used in an LLM? So, there are three different types of groups. There, where they show up. There is rotational positional encoding, rope. There's also permutation groups, translation groups. There are actually much more. So groups are very much used a lot in the internals of a transformer. And I'm going to look at the first example right here in this video. In other videos, we'll look at permutation groups, translation groups. So the first example we'll look at is a rope, which is a rotational position encoding. And this allows me to answer questions such as this word is before that word, or two tokens are 5 steps apart. So let's look at what I mean by that. Imagine you have like an embedding matrix like this. So you have a set of vectors like this, and what rope does is that it it slices this vector into pairs, into two-dimensional spaces. So when you look at this as it is right now, there's no information about order or position, and that's where we're going to encode. So what we're doing with rope is converting this into a pair of vectors in two-dimensional space. And then what we're doing is that we're going to apply group action to it. So what this does is that imagine this is represented by a vector like this. Because this is in two-dimensional space, we get a picture we could generate from it. And I could rotate this by some angle. And this angle is, we figure out this angle by looking at a specific frequency. So you'll see P is the position, and then you have a omega, and then you're multiplying that by W. And that right there is something that's unique for each position that we figure. There's a way to figure that out, the frequency right there. And that gives us the angle theta. So the angle is different for each type of vector based on its position and frequency. So what we're doing here is that we are then basically using that angle and putting it, in this matrix and getting some and transforming this vector and rotating it. And we're doing this for each of those vectors. What this is an example of is an SO2 group. And this is an SO2 group that we're applying to it. So the SO2 group, what that is basically this set. It's comprised of this matrix where the theta is a real number. So unlike the previous group in the beginning that we saw was finite, had a finite number of angles, where this is infinite. And I have a way to combine like certain angles here together. And you could like verify that this is a very popular group. This is the SO2 group that's used in quantum field theory. It comes up in physics a lot, so in particle physics. And it also is used in internals and in transformer. So what we could do is that with rope, what we're doing is that we're applying this SO2 group. So each of the pairs of vectors that we get, that we slice to, it allows us to encode information about order and distance. So what we are able to answer this question. So imagine you have this pair of groups, and we have angles for both of them based on their position and frequency that we're using to rotate. And what we do when we do a rotation, whether it's 20 degrees or whether it's 80 degrees, what we're doing is that we're applying basically that SO2 group to each of these vectors. So in this case, in the last example, in the first thing that we looked at, when we applied the group, what space did we apply to? It was this geometrical object that was represented by, the set X. And we're able to then apply that group action right there, right? And we're able to take a point in this space and then rotate it by some angle. We get a new point, right? So we do the same thing. We could take a group action. We could define a group action that is applied to each of those pairs of this vector. So we have sliced the vector right there into different pairs in two-dimensional space. And what we could do then is that we could apply an SO2 group to it. So when we apply an SO2 group to it, we get basically a another vector which is rotated 20 degrees. And then we could also do this to another pair, and this might be 80 degrees. So we're applying this SO2 group again. And it's interesting because the geometry is allowing us to encode information. So the other thing that we could do, imagine you have a vector A and you have a vector B, and it allows us to answer like information that B comes after A because B's embedding has undergone more rotation. So one was rotated 80 degrees, the other one was 20 degrees. So it allows us to encode information using rotations. So geometry carries the order in this example. And we're able to do this because what we're doing is that I have an SO2 group defined and applying it as an action to each of these pairs. So this is an example, very simple example of symmetries in an LLM. There are other examples we'll look at, which are permutation groups, translation groups, scaling groups, and this is it. I hope that was helpful. This is more of a mathematical way of looking at, the like applications of group theory inside of LLMs. Very interesting. Hope that was helpful. Thank you.